And this particular committee, headed by Mr. David Stringer, has really taken off and has blossomed as a subcommittee of the Government Relations Committee. And officially starting next year in 2019, it will be a committee unto its own, and David will be leading that as the chair. And so we're very excited. This is a topic that, and overall arching topic of microgrids and renewables that has really gained a lot of traction and really grown some legs of interest, and that's evident by the people participating in this audience today. So in this particular session here, we're going to be talking about remote monitoring, and keeping with the theme on some of the things that the Conference Planning Committee has tasked us to do is we had many of you were involved in the distributor dealer conference panel here just earlier. And so this particular group, and I'll introduce everyone here in just a moment, is a very interesting and very fascinating topic, and we're going to be looking at some case studies. So I'll kind of walk through a couple things here. But that's me. My name is Andy Briggs. I'm with Power Telematics. And we do generator monitoring, vehicle tracking, and all. And I've been asked, it's like a lot of things in a volunteer organization. You have to be careful what you say. Yeah, sure, no problem. Because when I was asked to moderate the general session panel tomorrow, they say, hey, by the way, we've got a couple of other panels that I'd like for you to moderate as well. So yeah, no problem. So glad to do it. So glad to be here. And my role is to facilitate the discussion and to keep things going here with the panel. So I'm honored and privileged to be here, especially with these distinguished folks here. So let me briefly go by and introduce each of our panel members. If you would raise your hand, because we're not in any kind of alphabetical order, but Edmund Campion, right here. He is Chief Engineer with APR Energy. Ed is an industry veteran in temporary distributed grid power in the global markets. He began his career providing temporary power for international stadium concerts, Olympic Games, live pay-per-view sports, Super Bowls, and awards shows on global TV. He is currently responsible for R&D, company technology strategy, power plant designs, including protection, automation, and controls, and the implementation of renewables. He also holds multiple patents for scalable modular temporary power plants and containerized natural gas power modules. Ed, thank you for joining us. Welcome. We're glad you're here. Next up, we have Harold Jarrett. Harold is founder and chief technology officer with OmniMetrics. And Harold has been immersed in the integration of power generation equipment. Oh, thank you. Yeah, I need to keep up here. Thank you. So if I miss one, just poke me. So Harold's been immersed in the integration of power generation equipment and wireless technology for his entire career. And Harold's a graduate of Georgia Tech with a Bachelor of Science in Electrical Engineering, a Master's of Science in Electrical Engineering, and I believe you also have an MBA thrown in there somewhere as well, and an active volunteer in robotics and STEM education. Harold is also one of our instructors for the EGSA Rally course for the advanced school, teaching the communications class. So Harold, welcome, and thank you for your participation on this as well. Next up, we have Matt Miersch. Matt, there he is. Matt's the product line manager for Basler Electric Company. Matt has more than 20 years of industry experience, beginning in a field service role. He joined Basler in 2000, and for the last 5 plus years has been responsible for identifying, developing, and marketing products for the regulation and system control product group. So Matt, thank you for your participation and welcome. And last but certainly not least, we have Anders Stelheden. Did I pronounce it? This is, thank you. Thank you. Anders, I'm not sure who else may have come the longest, but Anders is joining us from Sweden today, and thank you very much for your participation. HMS Industrial Networks, he is the product manager for HMS Industrial Networks, by the way. HMS is a Swedish-based public company with offices in 14 countries. The company headquarters are located in the city of Halmstad on the southwest coast of Sweden. With a background in electrical engineering and installations, Anders also worked within IT administration for more than 10 years, specializing in IT security, PKI, and wireless on an enterprise scale. Since 2011, he has held various positions within product marketing with HMS, with the last 2 years as product manager for the E1 business unit, where the focus is on remote solutions. So this is Anders' first EGSA conference, so welcome. Thank you. Thank you. So With that said, we have one more, certainly not last, but at least I need to scroll the page here, and that is our illustrious chair, David Stringer. So David is Business Development Manager for DIFE. DIFE is a Danish-based private company with subsidiaries in major markets around the globe. David has more than 40 years of experience with diesel and gas prime movers, generating sets, genset controls, and cellular technologies, and has been with DIFE for the past 9 years. He is an active EGSA member, having held director and committee chair roles within the association and providing guidance on a number of topics, including the renewables market. Dave is also leading the new Microgrid Renewables panel, as we talked about, as a standalone committee beginning in 2019. So thank you, gentlemen, for your participation, and very, very excited to have all of you. So in each of the panel discussions of today, one earlier in this one, we felt it important to at least define it, a few terms, so that we're all speaking the same language, so to speak. So we wanted to talk about the definitions, or rough definitions, and in this particular group, within with the types of applications, some of these may be blended or bridged. So in our distributor dealer group, they were pretty well defined, but remote monitoring, remote access, and remote control, so that when we're talking about these terms, that we're all kind of on the same page. So from a remote monitoring standpoint, we're looking at somewhat passive monitoring of the system, whether it's a generator set or a hybrid system. We're monitoring the activity and the status, oftentimes the device or devices reporting information back to a software platform, most often in the cloud, but maybe not. But the platform would maybe send out alerts and notifications and status update. Remote access is actually communicating with that a piece of equipment or multiple pieces of equipment and running the software either from your location to the system, no matter where in the world that it may be, or running software that is on and embedded into the controls and all of that. So remote access, often a point-to-point connectivity to access everything that's on board and on that system. And remote control is really defined as making the system or a piece of equipment do something. Most often it might be remote start and stop, controlling relays, changing all sorts of things, which we'll hear some pretty interesting, cool stuff today on that. But everyone felt it was important to at least just address and touch on a few of those terms. So the format of this panel is going to be a little different than the others. So since the topic of microgrid and renewables is so diverse, and there were so many applications, when we all as a working group decided, okay, how do we want to approach this panel discussion? It became pretty clear, and the suggestion was made, well, maybe it might benefit everyone first to have each of the panel members present a case study, roughly 10 minutes, give or take a little bit, but help us understand this wide, vast array of applications that, as opposed to trying to ask questions and quiz some of these people, the applications are almost as endless as your imagination. So we'll look at hybrid systems. It may include solar, wind, engine generators, many other types of renewables, as well as other power sources. So the format of this will be a little different. Each panelist will present a case study and to share with you demonstrating monitoring and remote connectivity in a variety of applications. So with that said, let's get started. So first I'd like to ask you, if you'd like, you can take control and I'll poke you if you need to change the...
So, thanks for having me on the panel. My first conference.
Welcome.
Really enjoying it. So, I'm going to start with this very rhetorical question.
Yes.
Why do we need remote monitoring? Obviously, without it, we're just guessing. We all know this. This is a quote from a guy called Peter Drucker. If you know him, he's born in Austria, I think, but he spent most of his time in the US.
Yes.
He said a lot of things, but some of them was quite good. It was really a coding machine. So with that said, I will show you this case study. We talk a lot about customer satisfaction. Here we have one happy customer, Mr. Hassan Shama. He is running operations for a company called Anywhere. And also in this slide, you see the, I'm holding the wrong gadget here, the net byte gateway that they are using for this application. There it is. And if you want to know more about the gateway, feel free to visit us at booth 7, so we can talk about this. Anywhere, of course, is a play of words. Energy, anywhere. In this case, also sustainable because it's renewables. The company is based in Dubai, but they have operations all over Middle East and also in the northern and western parts of Africa. I would say regions where most everything is remote. Is this too loud?
That's good.
Good? Okay. And they operate mainly off-grid locations. With that said, they also operate, some of them are grid-tied or could be grid-tied, but most of them are island. And basically all of them have solar, diesel, and batteries that will have battery banks. They have a large at least I think they have a large install base, hundreds and hundreds of sites, and they all are remotely monitored. And they have, I never seen a company with so diverse equipment. They have, I asked Hassan, they have over 30 different types of equipment connected. So anything from control panels to solar panel inverters, lots of power meters, solar radiation meters, and so on. So this is an overview of how this is set up. So if we look at that far end, we will have the equipment in the field. So diesel power generators, they will have solar panels with inverters. They will have tank with tank sensors. This is a nice gadget. Please check it out in our booth. So most of their sites, because we're talking about regions where you have a lot of sun. So they will run off the solar panels, charge the batteries. Sometimes it's not enough, so the diesel will start. If they didn't have, so really the challenge they have is to know when to refill the tank, because they don't really know how much diesel is running. Speaking of challenges, traveling with this in your carry-on, apparently it looks very interesting on X-ray. Trust me. And then we have the gateway that connects to all these equipment. The gateway is connected to our cloud. It's called Argos. And from the cloud, you have online dashboards, report generators, alarms, stuff like that. So in my role as a product manager, I do a lot of win-loss analysis, hopefully more win analysis and loss analysis. But I'm curious not only why we lost business, but also why we won business. So I asked anywhere why, and I said, we wanted, first of all, a one-stop shop. They wanted everything from one vendor. Oh, this is going by itself. So why? Because if they involve multiple vendors and something goes wrong, then the blame game starts. So if they have just one provider, there's no one to blame. They want it to be scalable, meaning that they start with one installation, and from day one, they are on an enterprise solution, and they can grow in this without installing or investing at their end. I mentioned that I have a lot of different equipment, so of course it needs to be vendor independent. And this is crucial for them because even we have nice dashboards on Argos, they needed to integrate with their own systems. So they needed us to have, and we have, an open API that you could use for integrate. Everyone knows what an API is? No one would dare raise their hand.
What is an API?
Good. You take one for the team. Application programming interface, making it possible for different systems to talk to each other in a standardized way. And then they wanted online dashboards. This is for their end customers. This is going amok. Sorry about this. this is for the end customers. They don't really use the online dashboards because they are integrating with the API. They needed some way of scheduled reports. They could use the API for this. Many of our customers do. They have a third-party report generator, and they just use the API. But also in Argos, we have a report generator. This is mostly for the end user again. They needed to have alarm notifications. So if something goes wrong, they need to be able to notify service technicians, also end users. So emails, SMS, RSS feeds, you know. And lastly, but not least, they needed remote access. We just defined what remote access is. So they will have equipment on site that they occasionally want to directly connect to, so they can upgrade firmware, reprogram, and so on. So I took a look at the anywhere.com website because, again, I was curious. And so I selected a few quotes, and I will comment on them. They now have standardized on NetBiter. They will put a NetBiter on every installation, regardless of size, which is a good thing for us. Since they have NetBiters on all sites, they collect a lot of data. I mean, huge amount of data. So they are building up a data set that they can utilize because they also have a big data approach where they analyze the data that they collect to suggest improvements. So what they do with this data is they are building a baseline and then they are doing simulations to optimize operations, see where they can make changes. And first of all, before they do anything, they make a baseline of like a year. So they will know when they make changes, they will know what results they get. Again, otherwise you're just guessing, you're trying. You have nothing to compare with. And if you want to know more about our remote solutions in general and remote management in particular, please go to the e1.biz solutions remote management website. You can read more.
Or stop by your booth.
You're welcome. And that's me.
Very good. Thank you very much.
Thanks.
Appreciate that, Dr. Basler. So next up, I'd like to call upon Harold Jarrett with Omnimetrics and kind of give us a case study overview of your presentation.
Okay, so knowing what's coming up after me in particular, Ed, we're going to see some large scale, I mean, I can't call what he does microgrid, but because he calls what he does microgrid, I'm going to call what I'm going to show you nanogrid, because I'm going to the other end of the spectrum. And because we have, again, a wide range of what's considered microgrid, basically I think it would be defined as a power generation system that's not tied necessarily to a grid, maybe optionally tied to a grid. And so I'm going to show you a couple of installations that are really small but meet that definition, because I really wanted to help define the fact that you can do this on a small scale as well. You can do it on a bazillion-dollar scale, or in my case, I'm going to talk about a hundreds to small thousands of dollars scale. And the things that I'm going to show you are based on these core, also micro widgets. So this is our core monitoring device, and what I'm going to show you is based on Iridium data. And so to distinguish this just a little bit, I wanted to make it clear that you can do this anywhere on the face of the Earth. You can do it on the North Pole or the South Pole if you want. You know, most of what we do is cellular, but we do satellite when you need to, and sometimes these remote prime power kinds of sites are just simply in far-flung places. So to implement a satellite connectivity, this is what it takes. You don't have a big dish. We're not talking VSAT with a big dish that you've got to point at a satellite. This is typical kind of iridium antenna. The iridium system is low Earth orbit, so they're spinning around the Earth. So this is all it takes. Mount this on the top of the cowling, put this widget on the inside, and the rest is just physical connection. Okay, so now we can talk about it. So all of these things are based on that hardware. And so again, very focused on the skinny end of the spectrum. The first one that I'm going to show is on a small island in the Bahamas. There is no utility whatsoever on this island. It's the primary source of power is solar battery and inverter, and then there's a generator for backup. And for my customer, the question is, what do they care about? They want to be able to know, did they size it right? Is it performing right? So are the photovoltaic panels doing what they should do? Are they providing enough current to make it through the night into the next day? Is the generator working? Is the generator capable of working? Does it have enough fuel and battery to be able to work? So way down at the very bottom of the Bahamas is this location. And its primary power plant is photovoltaic with a backup power of diesel. There are 3 subsystems of 6 kW each that are combined into a battery storage system, which is in round numbers 100 kilowatt hours of lead acid. And then because it's just a 240 volt single phase, the inverter is fairly simple. And then the transfer switch can pull genset in if the battery gets low enough to demand it. And so in this particular case, it was a 50 kW diesel. From my requirements, from our system, the little black box that you saw is this guy. And it's talking to an analog input module that allows us to pick up voltages from each of the photovoltaic banks, the battery itself, and then the AC output of the inverter. Likewise, the output of the generator and its fuel and, of course, battery. In fact, the system is powered by the genset battery. And it gives them, this very simple system gives my customer who has to maintain this far-flung system the ability to look at the gen battery, gen fuel, the individual values from the photovoltaics, and the current in each of the 2 legs of that single-phase system. Also, it lets them look at the battery bus in the primary energy storage system. So it's a 48 volt design point sitting at 52 volts in this case, so it's right where it should be. Looking over a period of a month, we can look at the voltages coming from the photovoltaics. And of course, you see day and night and day and night and day and night. So for them, they want to be able to zoom in. And in this case, the battery voltage is the gold graph, and the photovoltaic voltage is the blue graph. The PV is scaled on this side, the battery on this side. And so what we see is that the photovoltaic is providing, where are we? In this particular case, P1 is PV's blue. So it's peaking in the daytime in the middle 70s of volts, and then the battery charger is then applying that to the battery, which scaled on this side you see is running in the middle to upper 50s for peak. But here's the real key, is when the sun goes down, what does that primary battery energy storage look like? How deep is the dip? Is it making it down, making it through the night? In round numbers, with a 48 volt lead acid system, when you get down to 48 volts, you pretty much consume half of the capacity of the battery. So in this case, they're doing great. They're not stressing that system at all. So in this case, they sized it right, maybe oversized it, but they're not stressing their system at all. So another quick example, not so different, but in a very different location. Mountaintop tower, and there are cell towers and there are microwave relay towers that are up on the top of mountains. Of course, it makes sense if you're in the tower business, but there's no utility power available, so they're having to produce their own. And they too are using a combination of solar and generator. Similarly, they care about, if you're in the cellular business, or in this case, maybe microwave business, the base station battery is everything. Because if you run out of battery, you run out of data transfer, and that's a bad thing for them. So that's the number one thing they care about, is are they able to keep those primary batteries charged up? Is the generator working? Is the generator capable of working? The same basic kinds of things. It is way up on top of a mountain where you fuel it in the fall and you fuel it in the spring, and you don't do it in between because there's 20 feet of snow. It takes a snowcat to get there. So schematically, they're using both photovoltaics charging the battery system as well as generators. And they're using propane, and there are multiple tanks, which makes that step of gauging interesting. So 10 kW of photovoltaics, 30 kW generators, and in some cases they use a single, some cases they have alternating. I'm going to show you an alternating one here in a sec. The fuel supply and the transfer switch or a contactor, because among the other things here is the PLC that runs the site. And that PLC is the subsystem that has to determine, do I have to run my generator because I didn't get enough sun today? So it's really in control of the site. So the subsystem then that I was responsible for here gets data from the charger system by Modbus TCP. That's a very sophisticated charger rectifier system that's commonly used in cellular tower situations. Then we're extracting Modbus data from the gensets by Modbus RTU, a 2-wire RS-485 connection, really simple, but it allows us to get good performance data from those machines. And then probably the hardest part of all was collecting multiple tanks worth of fuel. Propane's not that fun to gauge, but then combining all of those tanks together to get essentially what you'll see as a sum of fuel, so that they can know, can they make it through the winter or not? So a snapshot here of the critical information that the customer cares about. Basically, we see the battery voltage, the battery current. The AC mains here is actually the output of the inverter, because there is no AC up there other than what you produce. The battery capacity and depth of discharge are related. Essentially, where is it in its state of charge? How much capacity is left at an instant in time? The output of the rectifier, and then the fuel, 1,750 gallons, we'll see a graph in just a minute. And then another important item for this particular one, you would think, why do I care about coolant temperature? Well, the reality is it's on the top of a very frozen mountain. And even though it's a propane-driven machine, you can't run a block heater 24 hours a day in a site like this. I mean, you have to put up much more solar in order to do that. So when the generator is needed, they have to, one, turn on the block heaters to get the block warmed up enough to comfortably start. And then there's this other thing that the propane, when it's really, really cold, doesn't vaporize properly. And so it required warming up a vaporizer subsystem in order to let the machine run. So coolant temperature is an important part of this application. And it's one of the more complicated parts as it turns out. Bottom line then is, what does the customer care about? Well, the site battery right up here is what it really is all about. Now, when you're charging lead acid, you commonly like to do that in a constant current sort of way. So what you see here is the genset current, and notice when it starts running, it has a reasonably flat top, substantiating that constant current charging technique. And as the battery voltage rises toward being fully charged, when it gets there, surprise, the genset current starts to decline, indicating that it's reaching full charge. When we get down here to the bottom, keep in mind that we're not just charging, but we're also powering the site. So that's why there's this baseline of genset current. It's not all just going into the battery. Similar to that Bahamian application, this is the real bottom line here. Am I making it from one cycle to the next, or am I discharging too fast? And so in this case, once again, you see that we're getting down to 24 volts. So at half capacity is looking pretty good. Then one other thing is the generator guys involved in this. Keep in mind, we've got solar people and battery people and cellular kind of people. The folks who supplied the generator, of course, are concerned, do we have it sized right? What's my load? Am I underloading, overloading? So this is a week or two of data that zoomed in. You can see this is an alternating design where one gen runs and then the next, and then it flips back and forth. So if we look at the peak loads on those two machines, sure enough, they're running right around 70% of rated load. Great number. You don't have to worry about the wet stacking situation. Of course, this is propane, but it's an appropriately sized machine. It's not being, there is no instance of being over demanded. Here's the fuel. You can see the fuel being added on the left and the consumption over a period of time, and this is critical to them because the idea of taking a snowcat up the mountain with fuel is not a popular idea. All of that stuff was showing things working well. Remember, we said the battery is discharging appropriately and charging properly. Well, sometimes things just don't go right. So what we see here is the genset battery in gold and RPMs in blue, showing the cycling of the gensets on and off and charging and discharging and charging and running and running and running and running until it doesn't. I had a fail to start right here. You can see the RPMs didn't get there, just did not light up. Once you get into a fail to start, that genset control is locked out and somebody has to go push a button physically. That one can't be recovered remotely. So then, unfortunately, when the genset stops working, the genset battery starts its decline. When you have no genset battery, you got nothing but solar, and you gotta pray for sun. So sometimes things go wrong, and of course, this is what remote monitoring is all about. And so that will tally up what it is on my Nanogrid application. And so the bottom line is you can do this kind of thing. We're very Modbus oriented, so all that data, that every bit of the data that you saw is the result of Modbus access to genset controls or chargers or other data acquisition modules. You can do it everywhere, and according to the spirit of the Microgrid group, it is examples of both solar and generation, and with some reasonable examples of performance data from those. So don't ask questions yet.
We'll circle back to that in a moment.
Okay.
Awesome. Thank you, Harold.
Right.
Appreciate that. So next we'll call upon Edmund Campion to talk about his tiny little application that he wants to show people about. So
Thank you very much.
thank you.
So we've heard a lot about time and collecting all the data. So on my side, I'm an end user. Why do we use SCADA and why do we use data historians? There's two distinct terminologies here. I look at SCADA as supervisory control and data acquisition. It's more what these gentlemen are doing, they're collecting data. And if you want to turn something on and off, you can do that as well. On the other side of it, we also run a data historian. So we, like you're saying before, we collect a lot of data off of our systems. But now you've got to analyze all that data. And most of the SCADA packages today are not designed for that. So using analytics, we try and predict issues that we're going to have in the power plants. Why collect all this data? This is an example of an existing power plant that we brought up online in August. It's a 300 megawatt. There's 256 power modules, a mixture of Caterpillar 3516Bs and MTU Series 4000s on the job site. We've got close to 340 alarm points, 600 data points, 135 analog data points. a lot of data, 4 big power transformers up from 11 kV to 230 kV. I've got 10 252 kV bays to interface my transformers up onto the customer's transmission line. There's a wrong number there on the bottom. We've got about 286 ABB protection relays across the whole site to protect all the medium voltage and the high voltage systems. You can't watch that on monitors and look for problems. It's physically not possible. You cannot watch 256 generators on a job site. You can't put enough people out there. So this is the whole reason why remote monitoring works. Collect all the data, analyze it with analytics in a data historian, and generate actionable events before you actually have an event. So real-time predictive maintenance. I don't want to get surprises. I want to know when my air filters are going to need serviced. I want to know when my fuel filters need service. I want to make sure my fuel tanks are getting filled at the right schedule and we don't run the engines out of fuel. I want to make sure that all this stuff is done and it keeps the availability and the reliability of the power plants high. Being able to use the analytics again and look at predictive, the delta P on my air filters is slowly increasing because we're getting clogged up. And is that unique in one area of the site? We got too much dust? Or is it internally in the genset? We got oil coming off the engine and it's clogging up my air filters. But we want to be able to predict that and then do a scheduled outage on the engine at my convenience. The maintenance staff can go out there, do the service work, bring the engine back up, and we're not waiting for air filters to fail and get ingested by the turbocharger, and now I've got a major costly event. I've got an engine down, I've got blown turbochargers, and I'm not generating money off the asset. Being able to look at historical data, how can we look at how the system is performing today, how was it performing last week? We can predict how it's going to perform into the future. I can also then start looking at comparing these engines and how they're performing on this power plant to how they were performing on their previous power plant, because it's all historical data. The way we do our data historians, we tie the data to the engine serial number for anything to do with the engine. We tie anything to do with the generator to the generator serial numbers. So when I take an engine out and send it back to MTU or to Caterpillar for a major overhaul, and I put in a new engine, that new engine gets attached to that asset number, and then we start tracking again new data. We do the same thing for our gas turbines as well. We got critical components there. We got the gas turbine, we got the power turbine, and we got the generator, and they're all serialized assets. I want to understand life cycle costs, maintenance, predicting maintenance, and the only way to do that is collect all this data and analyze it. This is a heads-up shot of the power plant where we're doing our customer testing in early August. We're up at 300 meg. This was a unique project. We had to hold 0.85 power factor at the interconnect. The contract was very specific. It's not what power factor you're generating at the generators. Regardless of grid conditions, we had to hold a 0.85 power factor. To achieve that, we didn't want to be pushing the capability curves on our generators, so we installed capacitor banks. So I've got two 50 mVAR, 230 kV capacitor banks helping to do power factor correction. And what that's helping me is when the power plant's up at full capacity, and if the customer does ask for that, I'm now somewhere about a 0.82, 0.83 power factor on my generators, and I'm not stressing the electrical system. If the customer hasn't asked me for power factor and we're running the site up at, let's say, 0.95 power factor, the generators are all running at unity because they don't have to make any VARs. It's all being done by the capacitor banks. I'm saving fuel. So as we all know with generators, unity power factor to 0.8 power factor, you're looking at 1% fuel savings and efficiency. It's also the engine's working 1% less as well because it's more efficient in converting mechanical energy into electrical energy. But being able to monitor the whole site and see what's all going on and making sure that this is transformer 4, 3, 2, 1. There are 3 winding transformers, so we're able to make sure that we're keeping our transformer secondaries balanced as well. We have on-load tap changers to try and maintain the correct voltage on the 11 kV side of our transformers so that we're not stressing the electrical system on the other side and help us maintain efficiency in the system regardless of what the grid voltage is doing. This is just jumping down into one group of gensets. Right here, we're running everything's running at about 0.92, 0.91 power factor. But this is all being done fully automatically in the power plant. So I go to my master control system. I want 300 meg. I want you to run at 0.92 power factor. Start. No operators running around, starting and stopping engines. That's the SCADA part, supervisory control. So I'm supervising it and I'm controlling it and I'm telling it what to do, and then I'm monitoring it in real time. This is just a heads up of one of our, this is a Caterpillar, the 3516B, where we're doing turbocharger diagnostics. So we have a custom screen done in our data analytics program, and we're trending data over time. We're looking at intercooler temperatures, we're looking at oil pressures, we're looking at oil temperatures, we're looking at the power output of the machine, and we're doing that across multiple engines at the same time. And all that's being done in real time. We're not using any human intervention. We teach the data historian program, look for these parameters, and generate a work order in our maintenance system if something goes out of specification. Similar to the same philosophy we use for our gas turbines. This is a GE LM2500 family. Monitoring the turbine for its performance, we know when to take the turbine down to do a water wash. It's one of the terminologies you don't hear much in the diesel recip side. You'll hear about maybe in the larger engines where they have to wash the turbos on 8, 10, 20 megawatt engines, but not so much down on the smaller engines. We take the turbine down because we're getting a lot of dust. Even though we got really good filtration systems on the front end of the turbine, we still get dust particles collecting through and coming into the compressor section in here. And that's where we're concerned about it, because if that's not working efficiently, we're not getting the performance out of the turbine. So we take the system down, we wash it, bring it back up, and then we monitor all the key points as well. There's other diagrams that we also look after. This is what we call an annular combustor system. So we're looking at temperature probes all the way around the gas turbine and making sure that all the fuel nozzles are injecting the fuel and the water correctly into the combustion system, and that we've got an even flame front around the whole annular combustor to make sure that we're burning correctly and we don't have any issues internally. What I was talking about earlier, we got two major sections here. We got the compressor section, the combustion section, of the hot section, and then we got the power turbine, the high-speed power turbine section, and then we got the power turbine. The power turbine is, if you look at this, is a jet engine. It's suck, burn, blow, push, and then we take all that exhaust, we put it into a power turbine. The power turbine turns the generator at 3,600 RPM or 3,000 RPM. So we're dealing with high speeds. The compressor section can be running up to about 9,000 RPM. So it's very important to keep an eye on all the critical parameters that are going on in there. So with that, I'll hand it over to... Yep.
Fantastic. Thank you, Edmund. Appreciate that. That was excellent. Matt. Matt's up next. Matt.
Okay.
Try to jump the gun.
I'll get in there. Okay. As Andy mentioned, we're pretty unique in this panel, and I'm going to have to say Basler Electric does not manufacture remote communication devices per se, right? So if you ask me why I'm part of this panel, the truthful answer is somebody volunteered me to be up here, but realistically, Basler Electric, I'm going to look at this more at the control level and the remote monitoring. So what we'll do from Basler standpoint is we're doing the control at the local level, and then we're going to utilize some of the counterparts and colleagues on this panel, the equipment that they use. So my presentation is kind of to understand what we're doing at our level and the data that we're giving them that's going to be useful in the remote monitoring scheme. So in this particular case study, this was a university in south central United States. They had 5 megawatts of on-site generation. And the idea is they wanted to be able to support their local grid, their microgrid, but they also wanted to be able to intertie into the main grid, the macro grid and peak shave. They want to be able to do the islanding, and then again, that export power when those machines aren't being utilized. So some of the things that we have to look at the basic control level is we have to understand what the capacity is on site. So whether or not that's generation, if it's diesel gen sets, if it's storage, if it's wind, if it's solar, whatever's available there. We also have to look at the amount of storage, the capacity that's there, the amount that's actually there, and then understand our loads based upon different times of the year, different applications within that university. The loads are going to vary, and understanding how to take, whether it's diesel generation or if we have storage available, and utilize that to manage the loads that are local. And then also intertie. So when I want to operate and sell that power back to the utility, if I'm grid connected, I want to be able to manage that at the intertie level, and then also pull it out if the utility grid would become unstable and give me that resiliency of that microgrid per se, and transition back and forth. So here's an example. This is the setup that was at the university. They had 2 utility feeds. So we had 2 mains with a utility tie and 2 separate buses. These 2 buses fed various areas of the campus, and then each one, there were 2 sets of actually 5 resources. In this case, they were diesel gen sets, but they could be wind, solar, battery, storage. From the microgrid standpoint, they could be any of those things. Both of these, they had to have the capability of managing the load, so they would monitor the load of each bus and bring on and off the amount of power locally to support that load, and also intertie with the utility. But they also wanted to have the ability to take their utility grid and tie that back, their internal grid and tie that back into the utility and do peak shaving. So all that data from each of those resources, whether it be the resources distributed, the distributed energy resources, the buses, they wanted to monitor all these loads. All those things have to be monitored. The breaker statuses and synchronization across any one of those utility ties are all tied together, and all that data is communicated between each individual control system and control scheme, and all that data is then given back into a main hub or SCADA system, which can be remote monitored. So all of this data can be tied remotely. In addition to just that, to doing the control, they're also looking at a lot of the things that were mentioned here. We can look at fuel levels. We can look at, understand the fuel levels on the machines. We can look at oil pressures, coolant levels, monitor all of that critical data. And that data is being gathered, at the control level, and then given back up into to the main level and remotely monitoring. So the controllers themselves, again, are all tied by Ethernet at the remote level. And again, they're doing the generator, the genset monitoring, the distributed energy resource monitoring and control. They're also doing the breaker control, the management. They're looking at import-export control and the local loads. So they're tied all in that, and they all communicate with each other. And then we can take, as I mentioned, that third-party device. They take that third-party device, and that goes out into the remote locations. So and then from a remote location, they can control, they can bring the particular resources on or offline, monitor the statuses for maintenance purposes, look at all those items, and make their controls from one simple location. So again, just kind of a recap. All the communication was Ethernet communications between all the resources and all that load management. So all that's being done at the Ethernet level. Monitoring the breaker statuses, monitoring the resources, and looking at the utility. All that's being done. The local control can be done, so the load sharing between those resources and looking at the loads, all that can be done at the local level, but it can be governed and monitored at the remote level through that remote monitoring system. So we also, and the key here with this application is they wanted to be able to monitor the power flow at the point of common coupling. So they were looking to export control and peak shave at particular times. So based on the amount of resources they had at that facility, they would export onto the utility grid and add additional support to the utility grid. And then on the reverse side, they would monitor the utility grid when they weren't tied, or when they were tied, they were monitoring the utility grid to make sure that they could remove themselves from that in cases of storms or isolate to make sure, and it gives that resiliency at their local microgrid. The control system and the remote monitoring had to be able to isolate in that condition, and it also had to be able to synchronize back into the utility. And then it also had to look at all of the alarms and statuses of all the components that are located within that grid. So that's also looking at all the utility ties, all the energy resources, all the loading, and all of that, any alarms that come from those things, and pull all that data back and compile it, and then move all that into the remote locations, or to the remote monitoring schemes. Okay.
Very cool.
So,
Thank you, man. Next up, Mr. David Stringer. We're going to share an application with us that's pretty fascinating.
Okay, well, Dive, what we've done, we've done a number of installations all around the world with microgrids. A number of those are remote monitored, especially over the Middle East and Asia. We're just starting now to do this in the States with regard to some microgrid applications, with remote monitoring as well. So in particular though, I picked out an application here which is, it's a movie of a rental company that's adopted our system here. It's not here, it's actually in Denmark, but it is a very interesting case study, and we've just released this on our website. So I've taken that video and brought it here. The company, it's a company in Denmark. They supply temporary power. They're like a mini Greco, I would say. They put power into events and other various applications around Scandinavia. And they have a big fleet, a very modern fleet, and they want to run that fleet as economically as they can and as efficiently as they can. So it's hard to see here because of this is a PDF of the case study, but you can see the sort of business they're in. They get a call, they come in, this is actually a rock concert, they come in and they can set this up in a couple of days. But you can see, how it's all put together. This is nothing new to you guys and girls, you've seen this all before, but the key is to getting the data it's very good. It's made their operations so much more efficient. And it's like, Edmund said, you can't keep going around looking at the gensets, which is what they were, to check them all. Now they can just sit down in the pub or at their home or anywhere they are and check this stuff and see what's happening. So you can just see, this gives you some of the idea of the size of the events that they do. But we'll get into the video because that really shows it very well. I gotta get into it.
Jeg har ansvaret for udviklingen af det nye generator-setup, som vi har i Godek. Jeg har været med til at bygge det op fra bunden af, og vi har i dag en flåde på omkring 75 anlæg, som vi lejer primært ud til festivaler, men begynder også at kigge efter andre markeder. Der er som regel en planlægning for, hvor meget strøm de skal have til scenerne, og så sætter vi dem op og kobler dem sammen og får det op at spille, og derefter så kører vi ud på langsiderne til boderne, som vi skal bruge en masse strøm til mad og holde fadøl koldt og whatever, hvad der nu måtte være af salt, der skal bruge. Jamen, der er vi så i den lykkelige situation. Det kræver noget strøm, og det er det, vi kan levere. Der går meget strøm på scenen. Altså, vi kører med 4, 8, vi kører med 11, 250 kWh på scenerne. Og hver anlæg leverer 200 kW, hvilket svarer til 375 ampere. I forbindelse med alle vores anlæg, der har vi valgt at køre med DEIF styresystem. Og i forbindelse med det har vi valgt et samarbejde med DEIF for at få lavet Onsite, så vi kan overvåge dem, altså fjernovervåge dem og se, hvordan og hvorledes de kører. Og det er selvfølgelig i opstart nu, men det ser meget, meget lovende ud. Når vi er på en stor festival, som Northside her, jamen førhen, der var det ikke unormalt. Vi gik 12, 15, 20 kilometer om dagen i runderinger med at kigge til maskinerne. Det kan vi begrænse meget nu, fordi at vi kan sidde med computeren og følge med i, hvordan det står. Vi kan også følge, hvad status er med brændstofbeholdning og lignende, og planlægge, hvornår skal vi tanke, og hvornår skal vi gøre det. Og lige så snart, at der er et eller andet form for problem, jamen, så får vi med det samme en alarm, som vi kan rykke på, og det gør, at vi kan gå ud lige konkret til den konkrete maskine. En festival som den her kører der 26 anlæg, der står spredt over hele området. Vi kan sige konkret, jamen det er den maskine, vi skal ud til, det er den, der er problemer med. Og det er et virkelig, virkelig godt værktøj, som jeg venter mig rigtig meget af. I forbindelse med Onsite har vi kigget på muligheder, og der har vi fået indbygget i alle vores anlæg Power Management. Power Management gør, at efterhånden som belastningen de falder, så vil vi kan stoppe maskiner ned og derved spare diesel. Og specielt som en festival her som Northside, som er meget grønt fokuseret, der lægger man meget vægt på at køre så økonomisk som muligt. Og det er et system, som vi har også i samarbejde med DEIF fået udviklet, så det kører rigtig godt. Derudover har vi fået lavet et system, som vi kalder koncert mode, sådan at trykker på en enkelt knap, så starter alle anlæg. Det vil sige, at man har fuld backup i forbindelse med musikafvikling på scener og lignende. Og det er noget, som vi forventer os rigtig meget af, men det er også noget, som flytter vores marked fremover, fordi at jeg har en tro på, at vores anlægsstørrelse, det bliver formentlig 100, 100, 250 kW, så bliver de bare sat sammen som bygklodser, i stedet for, at vi har nogle meget store anlæg. Det gør også vores flåde meget mere fleksibel over for kunden, så det er en kombination, som også giver en god markedstilpasset strategi. Det er et rigtig, rigtig godt setup. Jeg har trods alt, altså jeg har arbejdet i 25 år med det her, og det her, det er suverænt, det er bedst sat op. Også selvfølgelig bygget på den erfaring, plusser og minuser man har, og der har man forsøgt selvfølgelig at integrere flest plusser i det nye setup.
I knew a little more Danish than I thought. I call it whenever and power management. So
Set up.
Set up. I caught that. So surprised. So thank you, gentlemen, for all of those. I mean, again, one part of the intent of all of this, from a presentation standpoint, was to give everyone a wide variety of case studies. So that was pretty wide variety, I think, from nanogrids to macrogrids to microgrids, I think. So all points in between. So at this point, we do have a little time. I'd like to open up the floor for any questions, specifically of anyone in particular here. But we'll open up the floor for questions. I don't think we need a microphone at this point. It's a small room, but does anyone have any questions? Yes, sir.
Yeah, I've been to a couple of microgrid meetings. They had one in Homer Energy, had one in Denver last year. And one of the things they really commented on, they kept saying dirty diesel, which is what Jim mentioned this morning in his presentation. But they also trying to clearly define that a microgrid, in their terminology, in the industry, seems to be including battery or solar. So if it's just a group of parallel gensets, we've been doing that for years, and there's nothing really outstanding or new technology there. There's a lot of things going on as far as remote monitoring and control and power management and all that kind of stuff. But a microgrid, and I hope the focus of this committee becomes microgrid with the intention of integrating additional energy sources other than rice.
So you're more focused on hybrid.
The industry is.
Yeah.
As an individual, as a company, we're focused on that, and as an association, we're focused on rice. But the industry, if you talk microgrids outside this group, they think a group of parallel gensets is not a microgrid. Now, we can debate that because the city of Fort Collins thinks they're a microgrid. They have coal, and they have diesel, and they have solar, and they have everything else. But the microgrid community tends to favor the definition to include some inverter-fed generation from battery or solar or wind or something else.
Yeah, that is our intent. It is the second one. It is to bring all those renewable sources in.
And that's a huge opportunity for all of our members, because this microgrid business is headed up to the right and in a lot of areas, and integrating those is a key factor.
And as you know, it's been a hard job for me personally to get this pushed through because nobody wanted to listen about this thing.
Right.
So it was just pure diesel and gas.
You were finally you broke the camel's back. A lot of us have been preaching for this for a while, and finally you were able to get this going. I'm glad to see the membership involved here, and that's where we should be headed.
Yeah, thank you for the support. Yes.
Quick question, David, and to all of you. The microgrid I've experienced in the past was delayed due to the pricing of natural gas. When you're talking microgridding, putting them on actual locations of the buildings, not these prime sites, these multiple megawatt sites. And when we're talking in the city, we're talking putting generation at the building level with utility permission, which run obviously peak shaving from that point of perspective. So I didn't see any of that. Yet microgridding, when we get there, I mean, we've tried in the past, it's going to come back. But I want to see it at the building level, not at the power level, not at the plant level, but bring it down with the true necessity. 4 towers, 1 generator plant in the middle of these towers, feeding, for example.
Yes, and some of those opportunities will be explored here, definitely.
Both in gas and diesel.
Yes.
I have another comment from Andrew.
Yeah, so the case study that I did with Anywhere, most of their sites are rooftop. So they would have, so definitely buildings, because they would have solar panels on rooftop.
And working with the grid.
No, in most cases there are no grids.
Well, hence my point out in the microgrid at city level, right?
Okay.
Property becoming less and less in the city, so they use a building tower. Top of the building, you can use multiple technologies, which is fine, but you still have to communicate with utilities to transfer that power and run 24/7, so keep shaving. So that's sort of the microgrid I'm seeing in the future,
Right.
versus the multi-megawatt power.
No, exactly.
Question back here. Yes, sir.
Hi. Back in the old days, when I was a manufacturer, we had this discussion with power companies. And I think the message has been lost because originally they thought DER was a combination of everything. And it was not just localized to a building, it was a small region, like a neighborhood or a complex of buildings. That's what they regarded as a microgrid. That's what they believed it to be. But over the past couple of years, I've noticed there's been a shift, and it's changed to people starting to use that as a buzzword when they're talking about their personal buildings and using their microgrid, which is a bunch of DC power sources tied to a lighting system, which doesn't sound to be exactly accurate to me. Because when I used to develop, and microgrids are not just recips, and not just large gas turbines, they're microturbines. There are other kinds of distributed sources, but they're all working together in a cooperative network on a small region for power.
Exactly. Grid or islanded, yes.
Yes. I just want to mention that real quickly. So we're going to have a microgrid renewal committee that really kicks off in the spring for 2019. This panel is under renewables and microgrids committee, but it's more about remote monitoring. So we're going to have a lot more discussion about what microgrids are starting next year. I think, with these great presentations, we should try to focus the questions on the remote monitoring and telematics more than microgrids right now. I want to have all these conversations, but let's hold them off until the next meeting where we'll really focus on the renewables and microgrids and bring them all together.
And we can define that more then at that time.
Yeah.
Yes. Yeah, exactly. No, good point, Mike.
Great, thank you, Mike. Any other questions for the panel? Yes, sir.
Just a question for Edmund. I was intrigued by the applications that you were showing, and particularly some of the advanced diagnostics you were doing. Turbo is an example. How much? I mean, obviously your organization has a lot of deep domain knowledge and technical experience. How much collaboration with manufacturers do you do to develop some of that sophisticated diagnostics or even prognostics? Are you entirely leave it up to the data scientists to find these?
No, we work hand in hand with Caterpillar and MTU. So working with Cat, an example, we had a 75 engines in Myanmar running on natural gas, so G3516Cs, a lot of sensors. We ran that site for 4.5 years. We had 0 engine failures because we were doing all the monitoring. We sat down with Cat, looked at all our knocking events, we looked at our spark plug ignitions, we looked at our exhaust temperatures and worked with them and looked at, okay, what are we within spec? And what we discovered is Cat was telling us our knocking events are fine. They're low, but what we found was if we paid attention to them at lower levels, the engines were running more stable and we were running a lot more efficient, and the end result was more reliability for us. We weren't waiting until they said, okay, a knocking event 4 or 5, that's when you should take the engine down and check your valve lashings, check your spark plugs, make sure they're okay. Using enough data to show us, yep, fuel efficiency is a lot better when we do the maintenance on the engine. And there's some of it you follow with the engine manufacturer, some of it you follow with data. Another example of that would be, like I said earlier, we take the engines back to the Cat for an overhaul, or we take it to the Cat dealer for an overhaul. We take the MTU engines back to Germany. We send our teams in when they're doing the teardowns on the engines. We have all the oil history. We have all the maintenance history. Now let's look at what the iron set looks like inside the engine, because we don't do full teardowns on the sites. We'll do a top end on site, but not a bottom end. And what that's helping us do, and is helping Cat and MTU do, is they're now pushing out time to overhauls on our fleet, specifically for us, because they're seeing the wear patterns on the iron set that supports, yes, you're doing constant loading. We're not doing flexible loading constantly like peak shaving. We're up at 1450, 1500 kW, and we're running the engine solid at that for long durations. We're ramping the engines up slowly and ramping the loads up slowly. So we're giving the engines time to build up oil pressure, build up temperature, and then bring them up to full load. We're not an emergency standby where you want that engine up in 7, 8, 9 seconds carrying full load on a hospital. That's not our business. That engine has to do that maybe a couple of times in its life. So you don't care about the accelerated wear and tear inside in the engine. So definitely collaboration and a good partnership with the engine manufacturers is very important for us. The same thing when we go into our gas turbine, sitting down with Pratt & Whitney or sitting down with GE, looking at what's going on in the hot sections, looking at vibration monitoring. It's collaboration. Yes, we know a certain amount from our staff on site and knowledge learned, but they know what's going on. They know what the design criteria for those components are. So you have to work with the OEMs to share the knowledge. And then we end up getting a more reliable product at the end of the day.
Did you share the data back with them?
Especially oil analysis, because that helps them look at the wear metals in the engine, and then they know that the signatures of those wear metals, what that's coming off of. Is it piston rings? Is it the bottom end bearings? Is it top end bearings? You know, they know the metallurgy in the engine. We don't. We can make assumptions that that doesn't look good. I mean, over time we see that, you know, we replace an oil cooler. We know for the first 600-700 hours after we replace an oil cooler, we're going to get a lot of copper leaching. So we see that in the oil analysis. It's not critical, but we know we've changed the oil cooler. We're seeing copper leaching. It's not a stress point for us. So that's having data over a large, long time on a fleet of product and being able to make educated decisions based on data, not, oh, we think it's this. No, the data is telling us this is what it is.
That's fantastic.
And then teaching the data to look at that and generate work orders automatically as well.
Right. Bo, did he answer your question?
Yeah.
Okay, awesome. We have a question back here, and we have one more over here.
Who owns the data in your applications, and are you contractually doing anything with your customers on that?
So I would say our customers definitely own their own data. We are just harboring it for them.
Same for us.
I collect and own my own data.
Yeah, they own the data, yes. But they can share it with us if they want to, yes.
Did that answer your question?
Yeah.
Great. We have another one back here.
All right, two-part question.
One part, in using remote monitoring software and so forth, I understand a lot of it's all cloud-based. VPN and using cradle points, cellular cradle points for the communication aspects of it. What do you think would probably be pros and cons wise or so using cloud-based application reporting? Everything goes to your guys' servers versus single instance application, and just using cradle points and VPN back to whoever's doing the reporting and monitoring. What do you think would probably be the best security-wise and or functionality or scalability-wise?
Let's have Anders answer that one because that's
so
right
that's
in
a
his
question.
wheelhouse.
Yeah, that's a question we get quite regularly. So can we buy, our cloud is called Argos and it's hosted on Amazon Web Services. So we have redundant servers all over in all regions, 24/7 on-call duty and so on. So they say, can we buy this in a box and install it on our servers? And we say, you could, but you won't. Or you couldn't because we don't allow for it. They can, only one time I have been proven wrong, because normally we say you would never be able to set up a system as resilient as the one that we provide. And also when you do a cloud solution, you share the costs with all our other customers. It's extremely expensive and complicated to set up a redundant system like that. Okay. Only once was I almost proven wrong when I visited a customer in the US as a fact, and they might have pulled it off. Quite impressive, but no. Cloud, really, if you can elaborate on that question, sometimes customers ask, where is my data? So someone would argue that there is no cloud, it's just on someone else's computer. Yeah. That's an old one. So if you're using a cloud solution, it shouldn't really matter where the data is. That's my view.
So I just wanted to add in that case of a cradle point kind of thing, that implies to me that you would be running something like Modbus TCP over the air.
Whatever application it would communicate to whatever control panels are trying to connect to via cradle points.
Yeah, so anyway, I happen to be pretty sensitive to Modbus TCP risks when it's network connected. But also it implies to me with Cradle Point, which is a wonderful product, if you're connecting to it as opposed to it connecting to you, if it's set in a mode where you can make the connection to it, then somebody else potentially could too, and particularly dangerous if you are wired in for Modbus TCP on the downstream end of the Cradle Point, because somebody with malicious intent can wreck the machine.
Even through VPN tunneling and security applied to?
You just have to be extremely careful because you're exposing the inner workings of the genset control when you have a full-blown network connection to it. And I am capable, if I were on a network where a machine is tied to that network via Modbus TCP, I have the ability to change settings in that genset control, start the generator, and wreck it.
Yeah.
So you just be really careful about how you expose the equipment to a network.
And I'd say as well, if you're doing VPNs, you want to do hardware VPN at your site with all the security and all the antivirus, and there's some really good manufacturers that that. We have that done in all our power plants.
Stuff like that too.
Yeah.
So if your genset stops working, it was Harold. He dialed in direct into it. We have a question over here.
Yeah, well first, I've heard the saying, you've seen one microgrid, you've seen one microgrid. And I think all of your examples were a great demonstration of that. But as you guys have experience dealing with microgrids, for the current telematic solutions that you have and what's available, have you come across any requirements or needs that you haven't been able to meet with what you have today?
Great question.
I'd say the one thing that we don't do so much is power quality. That's a different thing from what we consider to be power monitoring. And I know in our earlier session there was a conversation about power quality is really inspecting the sine wave in a real-time sort of way. It's a wholly different kind of thing. And I have encountered customers who are wanting to know power quality information. Tell me if I have a spike. And that's a different kind of creature than what I discussed.
I could admit, because I mentioned that this customer has, they have algorithms. They use our API, which we don't have in our cloud. We don't have any big data analysis capabilities. So, for instance, they have solar panels in the desert, so they get dirty, dust and sand, and that impedes the efficiency of the solar panel eventually. And of course, they are remote, so there is a crossover point where it makes sense to go and clean them. And you would argue, well, rain will take care of that. No, it's desert. So, so at some point, they need to go out and clean the panels. So they can just calculate, and they can predict when to go and clean the panels, because eventually they will need cleaning. So there's a trade-off. Okay, we lose efficiency, but it's still kind of good because there's a lot of sun. And then at some point, no, we have to go and clean them. So that kind of analysis we don't have in our cloud, but since we have the API, they are happy to take the data, make their own calculations, and come up with a result.
Great. Well, everyone, we appreciate your time and effort. It's closing in on 5 o'clock now. Gentlemen, thank you very much for your efforts and for your participation on this.